Why can you take KVL in a loop with the gate of a transistor? I mean, there's still a voltage drop between the two sides. What doesn't make sense would be to take, KCL and try to figure out the current going into it, because that would be 0. So there is a voltage drop between the two. Hotspot. Nobody is safe from Michael. That's unfortunately true. What's these Zoom surveys for? Just to kind of gauge the class, figure out what your interests are, your background for this first week, and tailor a little bit of my examples to them. Well, you can have a voltage drop between a brick wall and one wire. You can assign a potential to every place in the universe, Adrian. And if you have defined two different points, you can define the potential difference between them, even if that potential difference is 0. You're welcome, Adrian. All right, let me end this quiz and then I'll get back to chat questions. So share result. So again, these quizzes hopefully get to know each other, know your classmates at a broad level, and also helps me know who I'm talking to a little bit so I can be a little bit more relatable, as hard as that is. So Purdue areas of interest interest you? Well, given how many of us are compies, no surprise a lot of us are interested in 362 microcontrollers and 368 data structures. Surprisingly, the next highest answer was automatic control, which is feedback system analysis and design class listed here. That's great. I mean, our automatic control area of research could use a lot more people in it. Maybe a lot of people want to do robotics. The question is, do you pick an area of interest during undergrad? Yes and no. You never actually explicitly sit down with your advisor and say, I'm doing this area of interest, but when you're choosing your plan to study, you choose which of these courses are going to be your advanced doubly selective, or some of these aren't the advanced doubly selective, but are part of your curriculum. These are basically your gateways. These are foundational courses for these areas of interest, and they're all like 300. 20,002 is not mandatory for computer engineering? I thought it was. Pretty sure it was.
It is.
Okay, thanks. Interesting computer architecture is the way to work towards that as an undergrad. Yes, definitely. You want to take 362 as soon as possible, get 337 out of the way, and then get into ECE 437. That class is brutal. However, ECE 437 is computer architecture. You basically learn how to create your own dual core processor, which is a harder thing than most people get to know in any university across the country. Anyway, back to this. Maybe automatic control robotics people, or you're just interested in control of large systems. Cool. A few people. What's next? Microelectronics and technology. Hopefully, you guys have been enjoying the MOSFET talk. Power and energy systems. That's my secondary area of interest. So, working with motors and the electrical grid, electromechanical and electromagnetic systems. Yeah. Communications, networking, signal images processing. You'll definitely enjoy the later part of this course because it's a lead up to ECE 301, signals and systems. And then a few people want to do VLSI and circuit design. Hopefully you're enjoying this talk too. And then there's like 2 people that enjoy fields and optics, which is actually my primary area of interest. So yeah. All right, that's enough of that. So I do want to give a little announcement to the entire class, including those who are following along asynchronously. Yes, the first quiz is due. It opens at noon Eastern time today and closes at 11:59 p.m. tomorrow in Eastern time. So that gives you a 36-hour window in order to do the quiz. Now, you don't get all 36 hours to actually do the quiz. It's timed at 2 hours, but again, no one should need 2 hours to do this quiz. Like, it'll take some people less than a minute. It'll take some people like, maybe 10 minutes if you're really thinking it out. It's 3 questions. It's a multiple choice quiz. It's very conceptual. It's going to be very unlike the exams. However, we're going to get you used to using this time period. Yes, everything's going to be in this time period. So every week, just be like, oh my God, I have something I got to do for ECE 2002. This is just to get you trained so that no one, forgets to do an exam or anything bad like that. Okay, do we have any other procedural questions? Like, I really hope this first quiz goes well. We hopefully we worked all the bugs out of the system so that technologically wise it goes smoothly. Hearing no questions, I'm going to go ahead and share screen. Okay. So let's go back a little bit where we've talked yesterday. We talked about single transistor amplifiers, and we said there's going to be 3 basic configurations. Amplifying is the most common signal processing task. We have this very nonlinear equation for the saturation mode or the active region of a MOSFET. We're not handling the early effect right now because it's just a complication, we don't deal with for, these very, cursory introduction to everything. But, this is a quadratic equation in VGS. How do we possibly make it behave linearly? The answer is good DC biasing and small signals. So we introduced the idea of going from transconductance to voltage amplifiers by using a load resistance and then taking the output have a common terminal of the source. Then we talked about this voltage transfer characteristic and the different regions on it. Then we talked about biasing and how after we do our biasing calculations, nothing should be able to touch them because we're going to keep the same DC bias point, the same capital VGS, and then get the same resulting capital VDS out. Then we went through a derivation of the small signal condition we need to obey, as well as this new parameter called FET Transconductance, and the 3 major ways of calculating it, geometry and the overdrive voltage, geometry and the square root of ID, or both VOV and ID. And then we talked about the voltage gain for that, grounded source amplifier. And then we talked about the hybrid pi model, which has, gate open circuit with respect to the source, which the drain to the source has both this voltage control current source and this output resistance RO here. RO comes from the early effect. VGS comes from the normal saturation mode operation of the transistor under small signal operation, I guess, to make that even more explicit. And we talked about when making a small signal model, we're going to use the transistor with its equivalent circuit, replace independent DC voltage sources with short circuits, usually short circuits to ground, and independent DC current sources with open circuits. Then we have the low frequency equivalent T model, which has the exact same information as the hybrid pi model. It's just a little bit easier to use sometimes when the resistance is connected in series with the source external to the MOSFET. If you don't like the equivalent T model, you don't have to use it. Everything is equivalent, so you can just use the hybrid pi model. We talked briefly about active loads and how we want to replace resistors with more transistors. The maxim of VLSI and circuit design is basically transistors are cheap, always use them. If the cost is using more transistors, that's not a bad trade-off because each additional transistor is very cheap. We talked about why we need amplifiers, and we went over some basic amplifiers, including the definition of voltage, current, and power gain, as well as how you convert them into decibels. We talked about the interpretation of a negative gain and gains less than 1. We talked about the power balance equation for an amplifier in general, where you have the power supply by the DC supplies, the power in through the signal is the power delivered to the load plus any power that goes into losses. And then we can define the efficiency as PL over PDC plus PI times 100%, or since PI is much smaller than any of the other two, PL over PDC times 100%. Then we talked about how we use the voltage divider equation to analyze this voltage amplifier model. And then we have the open circuit voltage gain and then the normal voltage gain of the amplifier AV. And then what we want to do. 4 linear amplifier types: voltage amplifier, current amplifier, transconductance amplifier, transresistance amplifier. And how, we said the FET transconductance is related to this transconductance amplifier. You'll notice that our hybrid pi model looks very similar to this, except Ri in this figure is infinity. And how you can convert between one amplifier type and another. So that's the review. Any questions? Does VGS get shorted? No, VGS is across an open circuit. Remember, you have zero current into an open circuit, but an arbitrary voltage applied across it. And the dual statement is for a short circuit, you can have any current injected through a short circuit. However, the voltage difference across it must be zero. So you should never short VGS unless you're working with a depletion type device. In which case, yeah, you can get by with doing that in a depletion type device for very different reasons. Hopefully that answers Adrian's question. Any other questions? All right, let's tackle some new slides, starting with slide number 69. So the procedure for analyzing a single transistor amplifier circuit. So the first is eliminate the signal source and determine the DC operating point of the transistor. So if you go back earlier when we talked about how you do the DC analysis of MOSFET circuits, this is what you're doing. You completely turn off all of your AC sources. Step 2 is calculate the values of the parameters of the small signal model, in this case, GM and RO. Step 3, eliminate the DC sources by replacing each independent DC voltage source by a short circuit and each independent DC current source by an open circuit. Now we have 2 more sub-steps as well. So 4 sub-steps in total. So if you have a very, very large capacitance, like it says in the text of the problem, treat, this capacitance as infinite or very large compared to all the other elements in the circuit, something to that effect. If we have a very large capacitance, treat it as a short circuit. This is the sort of mid-frequency approximation. And treat large inductances as open circuits at signal frequencies. Step 4, replace the transistor with one of the small signal low frequency models. Typically the hybrid pi model is used whenever resistance is connected in series with the source. I don't need to have the slash emitter in here. Then the equivalent T model is preferable. And then step 5, analyze the resulting circuit to determine the required quantities. So voltage gain, input resistance, or output resistance. So as you can see, this is basically a step for making small signal equivalent circuits. So if you ever hear the small signal equivalent circuit, steps 2 through 4 deal with that. So as a reminder, here is a table from the Sedra and Smith book on microelectronics that determines, or that gives you the equation for transconductance and output resistance, how to deal with PMOS transistors, and it shows you the hybrid pi model, as well as, 2 versions of the equivalent T model. So this is another good summary for how you actually do problem solving or how you analyze amplifier types. The last slide of the types of amplifiers, I'm looking at Salem's question right now. Where is the summing and integrating amp? I mean, these are generic amplifier types with gains. If you want to have a summing amplifier, it would basically be a voltage amplifier with multiple inputs. And if you want to have an integrating amplifier, you would have feedback that includes capacitance in it. So this is like the model of the amplifier itself, like the internals of the op amp, not the overall circuit structure that goes into like making an inverting or summing or integrating amplifier. Hopefully that answers that question. Siraj, you had a question.
Not really.
Oh, you're good?
Yeah.
Okay.
Sorry.
Aubrey had a question. How will we know which T model to use? Both of them have the exact same information. I like the one where it's a current controlled current source. However, you can't use the one that's a voltage controlled current source. It really depends on, like, you know, you might save one step in your solution strategy, but like it doesn't make a difference which one you use. Because again, remember the other option is don't use a T model at all. I just like, you know, saying it's easier to use a T model, equivalent T model, whenever you have a resistance in series with the source. Okay. Single transistor amplifier configurations. So here we go. This is a slide that I put 2 stars on in my notes because it's very important. So this is a nice little summary of why you would want to use these 3 basic amplifier configurations. It's got their pros, their cons, their, you know, relative abundance. You know, if you can't figure out why these are useful after this, like, I'm not sure how well I can rephrase it. But here we go. So all amplifier configurations must have a circuit arrangement for DC biasing, even if when we first introduced them, we're not showing them there. What are we showing instead if we're not showing the complete circuit? What we're doing is we're showing the steps 2 through 4, which is the small signal equivalent circuit. So, you know, we're going to first focus on the small signal behavior of each amplifier configuration and then rebuild the complete circuit, you know, DC and AC, you know, after we see just the small signal behavior. And I will say that for whenever I mention, you know, a DC supply, it's very important to know that ground counts as a DC supply. It's usually used as our negative supply. It just supplies 0 volts. So keep in mind that, you know, ground counts as a DC supply for the purposes of this slide. So the 3 basic amplifier configurations, and we'll talk about them we'll talk about all of them. It's common source amplifier today, and then common gate and common drain amplifier today into next Monday. So for the common source amplifier, the input is between the gate and ground, and then the output is between drain and ground. That means the source is connected to a DC supply, maybe through a resistor. So if you have a source connected to ground per se, then you would have the source connected to what's called common, you know, another word for ground, you know, roughly speaking. So it's a common source amplifier. The source is connected to common. However, it's sometimes confusing to know which is which just by looking at which source is connected to a supply. Sometimes there's a resistor it's connected through. Therefore, I think it's easier to identify the single transistor amplifiers by where the input and output is. So the input goes into the gate or between gate and ground. Output is between drain and ground. And then I'll just skip ahead a little bit. Common gate amplifier, the input is between the source and ground, and the output is also between drain and ground. And the common drain amplifier, the input's between gate and ground again, and the output is between source and ground. A little bit different. So that's how you can identify, you know, each of these configurations, you know, without having to rely on, you know, memorizing topologies and having that sort of photographic memory. This is what you should be looking for instead. So the common source amplifier is our most common single transistor amplifier. Pros is it has a very high overall gain magnitude and a high input resistance. The cons is that it has a high output resistance and limited bandwidth. The common gate amplifier, again, has the gate connected to a DC supply, seldomly through a resistor. It's the least common amplifier configuration. The pros is it has a moderate gain and a wide bandwidth. The cons is it has a low input resistance and a high output resistance. The common drain amplifier is also known as a source follower. However, I call it the common drain amplifier or CD amplifier most of the time because I will like the parallelism between the naming of the amplifiers. The drain is connected to a DC supply seldom through a resistor. It's a somewhat common configuration with good input resistance, good nice and low output resistance, and then a wide bandwidth. The con being that it always attenuates. It doesn't provide any gain, greater than 1. Do we have any questions? Hearing none, and I'll ask that you speak up if you do have any. Let's move on to characterizing general amplifiers. So this should be a familiar looking circuit configuration where we have our source block on the left, the amplifier block in the middle, and the load block on the right. We use the Thevenin equivalent circuit of our source with VSIG and RSIG. Your book is rather pedantic about saying RS is only for source resistances, not for resistances in the source terminal of a transistor. I think that's kind of baloney. RS can be what it wants to be. I'll use RSIG for the source resistance because it's the Thevenin equivalent of our signals generator. And then I'll use RS to represent the resistance in the source. And notice that, this may not even be a signal generator. It could be the output of a previous amplifier stage if you're cascading one different single transistor amplifier after another. So the output is a load resistance, RL, which could be a physical resistor or the succeeding stage amplifier's input resistance. So yeah, we say Rn is going to be equal to VI over II, where VI is, the voltage across the input of the voltage amplifier, and II is the current being drawn into it. And then the input voltage by the voltage divider is this equation. This is a unilateral amplifier model, so that basically assumes that the signal flows only left to right. So that means the input resistance should be independent of whatever load resistance we attach. There's no feedback mechanism. We define open circuit voltage gain A sub VO as VO over VI when the load resistance goes to infinity. And then we also have this output resistance RO. The voltage gain of the amplifier proper is a long-winded term for AV, which is VO over VI when RL is in place. So this is just another voltage divider. Your book calls it A sub VI because it relates the output voltage back to VI. I'd prefer to use just AV. And then the overall voltage gain is going to be a capital G sub V, which is VO to V sig, which is, two voltage divider equations in there. Your book also writes it as A sub V sub S or A sub V sub sig, which basically says that how you relate the output voltage all the way back to your signal source. I prefer capital G sub V. It's less tedious than dealing with multiple subscripts. Is GV in the previous slide voltage gain? Chenjuan. Yes, GV refers to overall voltage gain in slide 71. Okay. So now on slide 73, I would definitely try to, bookmark this slide as well, because it talks about the common source amplifier, our most common single transistor amplifier. So on the top, you can see the small signal equivalent circuit, or not quite. You see what the small signal equivalent looks like before we substitute in one of our transistor models. So all the DC biasing has disappeared, and we're left with VSig, RSig, the transistor, this drain resistance, RD, and then the output taken from the drain to ground. So the output is VDS, the input is VGS. Once we substitute in the hybrid pi model, for instance, we get the circuit on the bottom left, which is VSig, RSig, and then we see there's this open circuit between gate and source. And then in our model, we have this voltage controlled current source, the output resistance from the early effect, and the drain resistance. Notice the source is grounded, so we just put the bottom of our hybrid pi model to ground. Now, we said that the common source amplifier is a really good gain engine. So we can achieve a large desired gain by cascading multiple common source amplifiers together. So if for some reason you don't get enough gain from the first common source amplifier, just use multiple in succession. So the hybrid pi model we use to analyze it. So let's look at the input characteristics. So if we look at Rn, we said that Rn is just Vi over II. So the voltage at Vi is equal to VGS. Okay, that's whatever we are going to apply through the signal. However, there's absolutely no current drawn because it's looking into an open circuit. There could be no current that flows through an open circuit. Current equals 0 through an open circuit by definition. Because there's no current through this branch of the circuit, that means there's no current through Rsig, which means there's no voltage drop across Rsig by Ohm's law. So that means Vi is equal to VGS is also equal to Vsig. So we're just applying the raw signal at this point in the circuit. And Rn is infinity, if I didn't make that clear already. The output characteristics. Now we look at the output of the amplifier and look to the left. So if we look left of VO, we see two resistances in parallel. We see RD, which is connected between the drain terminal and ground, and RO, which is also connected between the drain terminal and ground. So we get that the output resistance is RD in parallel with RO. And since this current must flow through these two resistances, which appear in parallel, we get that this output voltage is GM VGS, the current, times RD in parallel with RO with a negative sign because the current isn't forced to flow through the direction determined by our passive sign convention. It flows opposite it. So that means there's a minus sign out front. Don't get tripped up by that. So that means the voltage gains of the amplifier, AVO is just VO over VGS, which is VI, whenever we don't have a load resistance. So that's minus GM RD in parallel with RO. If we do attach a load resistance between the drain terminal and ground, that just means we have another thing in parallel. AV is equal to minus GM RD in parallel with RO in parallel with RL, our load resistance. And this is also our overall voltage gain because there's no input attenuation either. VGS is equal to Vsig, so our voltage gain of the amplifier proper, AV, is the same as our overall voltage gain, GV. Questions? Where is Rn in the diagram? So let me see if I can get preview to respond. Oh, nope, that's not what I want. I want editing, freeform. So There is what Rn is. It's the sort of equivalent resistance looking into the gate of the transistor. It's not a physical resistor with a with a value printed on it that's Rn. It is instead the input resistance looking into the amplifier. Should we assume Rd is infinite? No. Rd is a resistance that comes from a physical resistor. You should not assume it is infinite. Is Rn always infinite in this model? Yes. Yes, it will always be infinite. Rn is infinite because no current crosses the gate? Absolutely. So that means if you were to measure the resistance between the gate and source of a MOSFET, if we were to physically take a voltmeter while the circuit was running, you would see that there's no current in there. So you would get infinite resistance if you were in ohm meter mode. In common source amplifier, Rn comes from the drain, right? No. Rn comes from the gate to source interaction. R out comes in part due to the drain resistance, not Rn. Who else has a question? Hearing no more questions, I'll go through a set of remarks. So, oh no, preview, don't misbehave on me. Turn off editing mode. There we go. So the common source amplifier has the advantage of a moderate to infinite Rn and a high gain magnitude. It's negative, which means it's an inverting amplifier. However, you might get a number like -50 out, which that's pretty good. That's a pretty large amplification of a signal. Disadvantage is that it has a very high output resistance. And if you recall, if our overall voltage gain, when we attach a load, we want to have a high output resistance so that when we have all these things in parallel, we get RO in parallel with RL. If RO is too small, that means it's limiting the amount of gain you can get and making it worse when you connect subsequent amplifier stages. So, I misspoke. Let me take that back. You want a very low load resistance, you want a very low output resistance instead, so that when you connect, this term is basically 1. RL over RL plus RO is basically 1. So you might say, okay, what if we just choose a very small value for the drain resistance? Well, if you do that, it's going to lower your GM when you actually calculate your value of GM, and it's going to make all of your gain smaller. So you're trading off gain for a better output resistance performance. The way around this is to use a common drain post amplifier instead. Something you can't tell from this picture or any of our analysis so far is the common source amplifier has an inherently limited high frequency response. Bandwidth is poor. That's where having common gate amplifiers can help out. So that's some remarks on the common source amplifier. Why does lowering RD decrease G? Ooh. We have to go back a ways. You know, I don't have a good answer for you right now. Let me get back to you in an email or at the end of lecture or June. I have to think about it. It's been a while since I thought about that answer specifically. Yeah, sorry. It's just I don't want to mislead you by trying to figure it out on the spot. So if you wanted to say, okay, what does this amplifier look like if you were to actually breadboard it and care about both the DC and the AC components, here's what it would look like. So here we can see we were applying Vsig and Rsig, our AC signal, and then it goes through CC1, which is called a coupling capacitor, COUPLING capacitor, into this 4-resistor biasing network that looks very familiar. We've got RG1, RG2, RD, and RS. And then we have another coupling capacitor, CC2, at the output that separates RL from affecting the biasing. And we're going to measure the output voltage right here across RL. RG1 and RG2 provide a voltage at the gate, which combined with the gate to source voltage produces the control voltage that turns this on and causes a DC value of VDS. Now, RD is our load resistance, or not load resistance. It is one of our biasing resistances, and it factors prominently into our equations. RS did not appear in any of our equations. In fact, it was not in our small signal model at all. We just had a ground. So what gives? Well, the answer is we put this really large capacitor C sub S right here, such that at the signal frequencies, this capacitance is so large that it acts like a short circuit to ground by our small signal model. So that means at the signal frequency, the source looks like it has a direct connection to ground. It's like RS isn't even there. So RS can help us with biasing, but it's gone when it comes time to actually do the small signal model and figure out the AC properties of the common source amplifier. Next, what happens if we do the small signal equivalent circuit? Okay, let's remember our steps. Turn off all of our, we do our DC analysis. Basically, you'd only need to analyze the middle portion of the circuit, which is a 4-resistor biasing network. Everything else only appears in AC. So those would be off. And then we do our steps. So step 2 is turn off our DC voltage sources. I think that was step, or yeah, okay, no. Step 2 was calculate the models of our parameters. So from this, we could find GM and RO. Bear with me. Step 3 is actually helping us construct our small signal model. So we would turn off our DC sources. So VDD, remember, this is just a voltage source. Let me see if I can draw and not have it go horribly wrong. I always choose the wrong one the first time. Remember, this is equivalent to this poorly drawn voltage source. So when we turn off the DC sources, what we're doing is we're saying, get rid of this. This becomes just a short circuit to ground. Okay, come on, preview, behave yourself. The same goes for the other voltage source here, VDD, it's the same thing. So it's going to get replaced with a short circuit to ground. We don't have any DC current sources, so we get to skip that step. The other thing we said was large capacitances like CC1, CC2, and CS get replaced with short circuits. So here, remember, RS in parallel with a short circuit is equivalent to a short circuit. This short circuit goes to ground. We don't have any large inductances in the circuit, so we don't have to worry about that step either. So what we'll see is, okay, we'll have V sig, R sig, a short circuit. We'll have RG2 go to ground. We'll have RG1 go to ground in parallel with RG2. And then we'll have our transistor model. We'll have the source grounded. We'll have RD go to ground in parallel with RL. And lo and behold, on slide 76, we get exactly that. The two gate resistances are in parallel. The source is grounded, and we have RD in parallel with RL. And we decide to use our hybrid pi model here for the transistor, which is the open circuit, the voltage control current source, and the output resistance. So if we were to calculate what Rn is for this configuration, we would get, okay, looking to the right of VI, let's bring back the editing tools and choose the freehand for once. Rn, remember, looks like the resistance looking in to the right of VI. So here we don't see just the voltage source anymore. I realize this may be contradicting something I said earlier, but we've fundamentally changed the circuit here. So for this circuit, we see we have RG1 in parallel with RG2 to ground, and then in parallel with an open circuit. Remember, anything in parallel with an open circuit is just the other thing. So Rn is equal to RG1 in parallel with RG2. Vi is equal to VGS is equal to V sig over, or times Rn over Rn plus R sig. So there's a voltage divider, which is found by getting the equivalent resistance here, Rn. Questions? Why is there RL in the equations on slide 73? I don't see RL in the diagram. Chen Zhuan, this would be if we attached one to the output. So we didn't deal with it, but pretend there's a RL connected to ground here. For any time we deal with voltage gain of the amplifier proper or overall voltage gain. Does that answer your question? Yeah. So it just clutters the diagram when you're first introducing the topic. But then when we come down to, I keep pushing the wrong button. I don't know the shortcut that gets you out of freehand mode. But then when we get to the screen amplifier, we show it explicitly connected because we have everything present here. Everyone's all here. The output resistance of this transistor. Now, this is where you have to be a little bit careful because most of the time they define output resistance as not including the load resistance. However, if they say the complete output resistance, they do. So this is RO, whereas this is RO, complete. If it will let me draw. Complete. So the output resistance defined here is RD in parallel with RO. If they ask for the complete output resistance, it's RL in parallel with RO in parallel with RD. That shouldn't say V pi here. That should say VI. Yeah, that should say VI, not V pi. So minus GMVI, RD in parallel with RO in parallel with RD. And then GV is the overall voltage gain. So that's our input voltage divider, Rn over Rn plus R sig, times negative GM RD in parallel of RO in parallel of RL. So as you can see, when we added in the full biasing network, we had the change to the input resistance term, which affected our overall voltage gain term. However, the output resistance and the output voltage equation look the same. That's what I'm trying to communicate. When you're measuring the resistance of resistor in parallel of an open circuit, that looks just like the resistance. So resistor in parallel of open circuit is just a resistance. Josh, GV is overall voltage gain. Yeah. So that's defined as the ratio of the output voltage VO to V sig, all the way back at the start. You're welcome. Is G something that'll be given? No. G is something that you calculate from the DC biasing. So remember, you can calculate what VGS is from here. And if you have VGS, you can get the overdrive voltage because you'll be given the threshold voltage of this transistor. So you can calculate, Kn times quantity VGS minus VTN, and suddenly you have what GM is equal to. All capacitors are replaced with shorts because we're saying these are very large capacitors. At the signal frequency, they behave like short circuits. What's the point of the capacitors? So the point of the capacitors is in their name. So for the bypass capacitor CS, it bypasses RS when you're doing the mid-frequency, small signal analysis. However, RS is allowed to help you during the DC biasing. It's very important to have RS because it prevents any sort of bad behavior when you're biasing. As for the coupling capacitors, they allow you to couple in the AC signal without disturbing the DC biasing network. So even though there's RL here, RL does not affect the biasing of this transistor. You only have to do the 4 resistor biasing network, not a 5 resistor biasing network, for example. Hopefully that helps you, Arjun. Okay. I'm going to go ahead and move on. So I'm in source amplifiers with a source resistor. So this is normally a problem that they leave for you on homework, but I decided to be nice and show you how you calculate this because I consider it an important enough configuration that I want to give you some hints on how to solve this homework problem. So we insert a source-degeneration resistor R sub little s in our small signal model. This is used for negative feedback. We use the equivalent T model to analyze. So the input characteristics Rn is equal to infinity for this simple example when you're not looking at the DC biasing network for a discrete circuit. And you see Vi is equal to V sig again. Now VGS is different because remember VGS, if I can draw, is right here. It's between the gate and the source isn't connected to ground, so it's going to be different from Vi. So the equivalent T model shows us that VGS looks like a voltage divider. It looks like Vi times 1 over GM over 1 over GM plus RS. This is the voltage divider formula, where if you multiply top and bottom by GM, you get Vi over 1 plus GM RS. or GMRS is unitless. The output characteristics, RO is equal to RD. We're neglecting the early effect because it makes things too messy here. So VO is equal to minus VI GM1 plus GMRS times RD. Where does that come from? Well, this current equals the current that flows through here, which is equal to, VI over this total resistance right here. And then that flows through RD, so that means we get a negative I times RD voltage right here. So the voltage gains of the amplifier, we get the voltage gain of the open circuit voltage gain is minus GMRD over 1 plus GMRS. And the voltage gain of the amplifier proper is minus GMRD in parallel with RL over 1 plus GMRS, same as the overall voltage gain. If you'll notice, what was the effect of including R sub little s? It was to take our equations from back on slide 73 and then add a denominator of 1 plus GM times R sub little s. So that's what happened here. To summarize what the source degeneration resistance did, 1 plus GMRS is the amount of negative feedback. So if you want to work your reasoning out, say ID increases for any reason. This is 382 type stuff, not something that I'm going to ask you to know on the exam. But if you wanted to justify it to yourself, say the drain current exists for some odd reason. VS equals RSIS does increase. Then because of that, VGS must decrease because, this voltage is being raised up. So that means VGS, which has the positive terminal at the same potential, but the negative potential is rising up. So that means the differential voltage VGS decreases. And then by our control equation, ID must decrease in opposition to our initial assumption. So that's negative feedback in action. Take ECE 382 if you need more explanation. RS is used to limit VGS from VSIG to prevent nonlinear distortion. So yeah, it curtails what VGS does. It extends the bandwidth of the amplifier to higher frequencies at the expense of achievable gain. So yeah, you're like, why would we do this? We're adding something to the denominator of our gain. We're making our gain magnitude smaller. Well, it makes our bandwidth better. So that's the beauty of negative feedback. We can get a trade-off here. Looking at this alternative equation, you can learn a little trick for how to calculate common source amplifiers quickly. Gain is the negative ratio of the total resistance at the drain. So that's the equivalent resistance at the drain, RD in parallel with RL, to the total resistance at the source. The resistance in the source is 1 plus GM plus RS using our equivalent T model. What questions do we have? Not hearing any questions. I'm going to use the last, 4 minutes and 50 seconds to cover a new amplifier then. So previewing some stuff we're going to discuss on Monday. Here is the common drain amplifier, also known as the source follower. So the source follower acts like a voltage buffer. It allows high impedance sources to connect to low impedance loads with almost unity gain. So just like, what's the point of the voltage buffer when we talked about ideal op-amp configurations? This basically acts like the voltage buffer for single transistor applications. So here we can see our small signal-ish model is VSIG with RSIG transistor. Drain is connected to ground at signal frequencies. And then in the source is our output across RL, a load resistance. Replacing the transistor with its equivalent T model looks something like this, where I've moved the resistance that's normally between this node and ground to the ground node that's down here, which is totally legal. I'm still having the same connection. It just ground from up there is now ground to down there. So the input characteristics, we're looking into the gate of the transistor. No current flows through the gate. Infinite input resistance. VI is equal to VSIG. Output characteristics. So we define the output as basically looking up there. And we see that the output characteristics is 1 over GM, a nice low output resistance, just like we want. Voltage gain of the amplifier. This requires us to look at VO. So this is another voltage divider, where how does VO compare to VI? Well, it looks like this equivalent resistance is the lower resistance of a voltage divider formed by RO in parallel with RL and 1 over GM. And so we just use the voltage divider equation to get VO in terms of VI. Divide both sides by VI, we get voltage gain of the amplifier proper. Doesn't include RL, but the overall voltage gain, which is the same as the voltage gain of the amplifier, is just this voltage divider type expression. The top diagram on slide 77 is the translation to baud diagram using the T model. Yes, yes it is. Same with slide 79. That's what this sort of statement right here is saying, where we use the equivalent T model. How we know the differentiate to know, oh, the top circuit is a source follower, is the ground on the top? Well, the drain is connected to ground, which is common, so it's a common drain amplifier. But remember, I like to say the input goes in between gate and ground, and the output is between the source and ground. That makes it a common drain amplifier. You know which, the other two terminals are the input and output, the one that isn't mentioned in the name of the configuration. What is RL for the common source amplifier? That's the load resistance. Here we have the load resistance explicitly connected. Otherwise, there really wouldn't be much for it to be acting on. It would just be acting on RO instead. And notice that GM over 1 plus GMRO is saying, hey, this is like having 49 over 1 plus 49. So this is a number that's less than, but mostly equal to 1. And basically we say that here. CD amplifiers have this advantage of high RN, low R out, and wide bandwidth, or those are the advantages. And the disadvantage is the output is just slightly less than 1. It's a voltage buffer in the output stage of multi-stage amplifiers, even for relatively large signals. So it works really well at that. They rarely get the spotlight. Instead, they work best supporting other amplifier configurations. So. Salem's question, G and S terminals are shorted. Are they? G and S are shorted. No, they are not. I don't know how to do that. This is the gate terminal right here. That looks like an O. Gate. That got replaced with a square. Gate. Gate. There we go. Source. That got replaced. Source. They are not shorted. They are connected through the resistance in our model. But there's no current that flows in. RL is load resistance. Yes, Shenjuan. All right. It is the end of the lecture time. If you have any more questions, I will try to answer them. I need to get back to Arjun about the question. Do not forget to take the quiz. Opens at noon, closes right before midnight tomorrow night. If you have any technical difficulties, let us know as soon as possible. Do not wait until 11 o'clock p.m. tomorrow night. Man needs notability in his life. Not sure what that refers to. Are you about to be in office hours? Yes. My office hours start at 11:30. So I need time to run from my apartment to my office. It does take a finite amount of time. No, 11 p.m. is an Eastern Daylight Time, EDT. All right, goodbye, everyone. You're welcome. I hope you enjoyed the first week of class. The TAs and I have really put a lot of effort into this. Hopefully you notice. Bye-bye.